Okay, now I will try to summarize what we have done under the project called Sigma and Share. These are two European projects, and they let us develop, they gave us the opportunity of developing predictive models, as you did in NJ West 1 and NJ West 2. So these are the 5, and actually Nico co-authored 2 of these predictive models. So, if I miss something, you can just stop me and complete it. Well, anyway, so essentially with different subsets of resource, 5 teams, 5 groups developed 5 different models. There are some similarities between NGA project, and there are some dissimilarities. So essentially, Akkar et al. And Bindi et al., we used the conventional approach. Okay, so we developed our models by using random effects regression methodology, and it's quite, in a way, traditional right now, conventional. The other 2 models developed by Deras et al. And Hermkes et al., they preferred using data-driven or non-parametric methods. And essentially, Deras et al. Used artificial neural networks, whereas Hermkes et al. Used Gaussian process method for regression. Essentially, if I understood it well, Hermkes et al. Wanted to emphasize the modeling difference in their approach. Bora et al., they did use random effects, but what they did, they estimate PSA using random vibration theory from the estimations of Fourier amplitude spectrum and strong motion duration. So they're using the estimations of FAS and duration through random vibration theory, and then come up with PSA. So this table, in a way, describes the overall, say, limitations of each method. The first column shows the number of earthquakes used by each developer team. The second column, number of stations used by, again, these GMPs. Third column, the number of records used by these GMPs. Here, I'm showing you the recommended magnitude values. So the ones in the parentheses are used while developing the models, but the ones which are not in parentheses, these are the recommended lower level and upper level moment magnitude values by each developer. And again, the same format for distance, recommended distance. The ones in the parentheses, the used upper and lower level distance measures for each distance values for each GMPE, and the ones which are not in the parentheses, they are the recommended values for distance intervals. And the last column here shows the recommended VS30 values. As you can see here, there is a clear indication of recommended VS30 only for 2 models. This is Akkar et al., which I tried to summarize in my previous presentation, and this is Bora et al., and they recommend the use of their model for VS30 values between 200 meters per second and 800 meters per second. Well, immediately, you can see that most of all the models except Hermkes et al., they use data more than 1,000 recordings. The recommended MW starts from the lower level is 4, and except Akkar et al., all of them recommend their model to be used up to magnitude 7.6. The recommended distances, the upper limit is 200 kilometers, except for Bindi et al., they are recommending it, the use of their model for distances up to 300 kilometers. So these are the, say, common points of the predictive models, resource predictive models. So all of us, we are using moment magnitude, Joyner and Bour distance, VS30, and geometrical mean horizontal component definition. None of us made a difference in terms of main and aftershock recordings, so we included all types of earthquakes in our in terms of main or aftershock in our equations. All GMPs include records with no excuse me, records with no measured VS30, and also exclude unknown style of faulting. And all GMPs estimate peak run acceleration. Again, all GMPs, but Bora et al. Estimate peak run velocity. Akkar et al., Hermkes et al., and Deras et al. Estimate pseudospectral acceleration between 0.01 second and 4 seconds. Bindi et al. Estimate pseudospectral acceleration between 0.02 seconds and 3 seconds. And Bora et al. Estimate pseudospectral acceleration between 0.02 seconds and 10 seconds. All right. Okay. So these are again the major features, but now the differences for each predictive model. So we excluded singly recorded events. We did not consider earthquakes for focal depths greater than 30 kilometers. We did not consider, we only included free field recordings. We included recordings of with all three components that, whenever all three components are available, because we developed another model as part of this study for V over H ratio. And we used Akkar and Boehmer 2006 criteria for usable period range. Bindi et al. Also excluded singly recorded events. The focal depths are greater than, that are greater than 35 kilometers are excluded. No free field recordings. I mean, all of them are free field recordings. All three components should be available again, and they used records with low pass frequency less than 20 Hz and spectral periods up to usable period range by implementing this formulation, which is 0.8 times the high pass filter period. Bora et al. Exclude focal depths greater than 30 kilometers. They also exclude distances without having RJB, and also records without two horizontal components. They have this criteria for excluding records in terms of filter cutoff. So whenever the Bruns source corner frequency for a stress drop of 100 bar is smaller than the filter cutoff, high pass filter cutoff frequency, they just excluded that recording. Deras et al. Excluded focal depths greater than 25 kilometers, and Hermkes et al. Did not consider, considered only again free field records. They did not include recordings with unknown RJB, and they considered only records with low cut filter values less than 0.25 Hz. Oops. Okay, so I think this part is the interesting part for you. So I'm showing the, say, comparisons for peak run acceleration for a generic rock-side strike-slip earthquake. The estimations of, say, these 5 models in terms of distance. And also, in these comparisons, though it's not very clear here, this curve, the gray dashed curve, shows the behavior of Buren-Atkinson 2008 model. Okay, these are the actually these plots here I'm showing you is from Douglas et al., which is going to be published in the same special issue. All right, so the first column shows the distance-dependent PGA variation for magnitude 5 and 6, and the second column shows the distance-dependent variation of PGA again for magnitude 7 and 8. So as you can, why we choose, by the way, Buren-Atkinson 2008, because our models are very simple in a sense, in terms of functional forms, and Buren-Atkinson 2008 has the simplest, say, functional form, and that's why we choose it for the comparisons with, say, previous NGA West project. So the decay rates and median predictions are very similar for magnitude 5 and 6 events, and the differences between the models increase with increasing magnitude and increasing distance. To me, if I'm not mistaken, this is something different what you observed in NGA West 1 project, because in NGA West 1 you were observing less differences for large magnitude events, so which is just the opposite in our case. And in my opinion, this is because we're adding more emphasis on smaller magnitude events. We have more smaller magnitude events than large magnitude events, and this could be the reason why we're observing, say, differences as magnitude increases. Oh, by the way, in all cases, as you would immediately notice, as distance increases, the Buren-Atkinson model estimates larger values, and this is because, as I tried to explain in the morning, for European data set, the attenuation rate, decay rate is faster than the other locations, I would say. Well, this is the magnitude scaling comparison again for peak ground acceleration, solid spectral acceleration at 0.2 seconds, solid spectral acceleration at 1 second, and solid spectral acceleration at 3 seconds. And again, we're comparing our estimations with Buren-Atkinson 2008. Okay. Essentially, all the models show nonlinear magnitude scaling, although, I mean, Deras et al. And Hermkes et al., they do not impose any, say, sort of functional form for magnitude scaling. The data itself shows a nonlinear magnitude scaling. None of the models considered magnitude saturation for large magnitude events. Essentially, while we are developing our model, ASP13, we tried a cubic magnitude scaling based on the studies by John Douglas and Jose. And but I mean, and then we observed some sort of oversaturation, or I would say supersaturation for high frequency cases, but then we did not want to include it in our model. Again,
what did you want? What didn't you include?
Sorry, maybe I'm running too fast. We tried cubic magnitude scaling, and we then observed some oversaturation, and then we said, I mean, we did not take that risk. We preferred using quadratic magnitude scaling with hinging magnitude. I mean, we did not essentially derive our regression coefficients for cubic magnitude scaling, which gives us magnitude oversaturation. Well, the differences become apparent for larger magnitudes here again, and as you can see here, the data-driven models, in particular, I think the one from Hermkes. Yeah, they have a very complicated magnitude scaling. There is some sort of fluctuation with magnitude. Okay, so again, this is the same type of comparisons for style of faulting. The first row shows reverse to strike slip style of faulting ratios, and the second row shows normal to strike slip style of faulting ratios. For reverse to strike slip style of faulting, as you can see here, the model by Hermkes and Bindi, they have they estimate reverse events significantly larger than the strike slip events. There is, I mean, almost all of the other models, resource models, they also have, say, reverse events larger than strike slip events, but essentially the level of, say, difference between reverse and strike slip is not more than 10%. But the other, not even 5 to 10%, I would say. But the other two models, they have a significant, say, difference with respect to the Akkar et al., Bora et al., and Deras et al.
And are those the
Yeah.
same data sets?
They are, I mean, the resource itself is a huge data bank, but each model developer chooses
Their
a
own
different,
subset.
exactly, subset. Yeah. For normal to strike slip events, the first thing that you would observe if you make a, I mean, really detailed comparison here, the first thing that you're going to observe is that Hermkes et al. Predictive model, Deras et al. Predictive model yields normal events larger than estimates, normal events larger than reverse events, which is not the conventional wisdom. You would expect just the opposite. This could be attributed to the resolution of style of faulting in their database, because there is very little reverse events in their database, and essentially this might be the reason why they're getting this result. Well, if you look at the variation of normal to strike slip ratios here, you would note that the predictive models driven by conventional methods, I mean the mixed effect regression methods, Bindi et al. And our model, the normal to strike slip estimations ratios are quite similar to each other. And one other thing, important comment, is Bora et al. They do not consider style of faulting in their equation. This is VS30 scaling. Again, Akkar et al. Is the only, say, model I would say that considered nonlinear soil effects. Bindi et al. And Bora et al. Predictive models, they disregard nonlinear side effects. The other two models, the data-driven models, they don't impose anything. They just indicate that the existence of VS30 and the data itself shows the trend. So essentially, we are the only, say, I would say, developer team that explicitly describe the nonlinear side effects. Well, if you, oops, sorry. Okay, so if you compare, oops. Yeah, if you compare these two plots, these are the, again, spectral acceleration ratios between 270 and 760, so generic rock site. And this is the spectral acceleration ratios between, say, 490 and 760. So the dispersion increases as the site gets softer. We have a, peak. All the models have a peak at about 1 second in terms of spectral ratios. And when you compare our, say, spectral ratios with the one suggested by Burr and Atkinson, the Burr and Atkinson site amplification for softer sites is significantly lower than our estimations here. Okay. This slide here shows the aleatoire variability. So again, almost all models, firstly, all models are derived independent sigma, because we don't have, large magnitude events in resource. Bora et al. Predicts larger sigma with respect to other predictive models, resource predictive models. There seems to be an increase in sigma with increasing period, except our model. But essentially, I would say that the dependence of sigma on period is insignificant, and we still have larger sigma with respect to NGA models. This is the variation of sigma for Burr and Atkinson, and these are the variation of these show the variation of sigma of resource models. Possible explanations for this significant difference could be, the difference between NGA models and resource or European models. High variability in ground motion, as data comes from different countries, so there is no quite a bit of standard in that sense, although we try to compile them and then we try to process them in a uniform way.
You're not saying that it's inherent differences. This is in the data collection and processing and that sort of differences?
No, it's the regional differences. So
But
maybe
Bohr's
the
model
regional
has regional differences in it too, right? They've got their
the-
global data sets.
I mean, the previous NGA models mainly focused on data from California and Taiwan, whereas now we have Italian data, we have Greek data, Turkish data, a few Iranian data. We even have data from Algeria and Egypt. So
Okay.
these may be showing up in the sigma, in the variation of sigma. And also we are, because of the,
But do you know, is this a tau difference or a phi difference? I mean, what's causing it?
I didn't do anything like regional difference in terms of, but I can do it.
Okay.
I can do it. It could be interesting. And also we are using we're using more smaller magnitude events, which could also inflate the level of sigma. And we are trying hard to improve the data quality here, but we may still have some problems with the metadata information as well, still. Okay, and these are the comparisons for response spectra. Again, for a generic rock site, Joyner and Bohr distance 10 kilometers and strike slip events, magnitude 5, 6, 7, and 8. I'm not going to say too much, something different than the previous slides. As magnitude increases, we start observing larger differences in spectral ordinate estimations. In particular, the data-driven methods, GMPs, they show significant difference with respect to other GMPs. We are good with, say, Bohr and Atkinson 2008 model for this distance range, but when we increase the distance, they will estimate higher spectral ordinates with respect to these European GMPs. And this is again something in line with the previous slide. Again, response spectrum comparisons. But now this is for soft site and this is for generic rock site. VS30 here is 270, whereas VS30 here is 760. Again, as the site gets softer, you start observing larger differences between the models. And again, the data-driven models show some unexpected trends in terms of spectral ordinates, because they do not do any sort of smoothing or nothing. I mean, they just, because of the methodology they're implementing. Deras et al. Predict a model. They may have some implications if they're used for softer sites and larger magnitude events. Essentially, Deras et al., the French group, they themselves indicate that their model should not be used for large magnitude events and softer sites, and they say it by themselves. So these are the conclusions. Estimates in terms of style of faulting. We're using the same data bank, but we're sort of gathering different subsets from that data bank. And we still observe significant style of faulting differences. There is a significant dispersion among the resource GMPs. And the dispersion is more significant in reverse strike slip ratios. And this is because we do not have too much reverse events in our databases. Bora et al. Do not consider style of faulting effect, they just neglect it. Hermkes et al. Differ significantly with respect to the rest of resource models in reverse strike slip and normal strike slip ratios. Deras et al. Estimate larger normal spectral ordinates with respect to reverse spectral ordinates, which is just the opposite of expected trend. And Binde et al. And Akkar et al., as I tried to emphasize, yield similar normal to strike slip ratios. And if we compare our normal to strike slip ratios with Boer and Atkinson predictive model, we observe that there is significant difference between Boer and Atkinson and our models. Other important remarks: all resource models yield similar spectral estimates for moderate size events, but the discrepancy between the models increases for larger magnitudes, longer distances, and softer sites. The variations in spectral estimations of resource models are higher than those observed in NJ-West1 GMPs, and the major reasons can be we are using different techniques while developing GMPs. So some of them are using data-driven techniques, some of them are using conventional techniques, some of them are using conventional techniques but estimate spectral acceleration from different tools. So this could be one reason, and we have also large amounts of poorly recorded earthquakes in our database. This could be another reason of large discrepancy. Then again, the standard deviation of resource GMPs are higher than the NJ-West1 models. Actually, it's the between event sigma that varies from the resource GMP.
That's the tau, then you're saying,
yeah.
is the term?
Yeah.
All right.
All right. And these are the references that I used in the preparation of this presentation.
So thanks. We are way behind, about an hour. We're going to have to figure out how to catch up a little later. But let's get through some discussions with our responses before lunch, or questions for Sinan. And I would start with those other models. Would you be recommending them? Do you think they're ready for application?
The data
for our problem, which is, I think
okay.
you know, one is close distances, large magnitudes, and the other is going to be background zone normal faulting.
I mean, the approach that is used in resource is quite different than the NGA project. I would say the resource GMPs, some of them are pure research purposes, for pure research purposes. For professional implementation, you may have some reservations.
So
in that sense, I
put you
would
on the
say
spot. Which ones would you
Binde
use?
et al. And ASP13, you may consider those two GMPs for your testing and evaluation, but the other ones, they may have some implications in the application for PSHA.
One question.
Yes.
So,
Yusuf, you need a microphone. You can start with you, Steph. I don't know. Bob, do you have anything?
Or should I wait? Should I wait? Oh, Sinan, I want to make sure. Did you say that your model for the reverse fault, you don't recommend to be used because you have only...
We have, exactly. I mean, when you just look at the overall, say, behavior in the trends, and when you look at the residual analysis, I would say for reverse style of faulting,
less reliable.
Reliable.
Then quickly, I want to go over this. So you mentioned that you used only measured VS30,
Exactly.
but you use Iranian data. I know for a fact they don't have VS30 measured.
They have for few stations.
Few stations. Okay. Then one last thing. So since for your model, not the other models, you used mainly European data, do you recommend your model to be used for different parts of the world also or not?
I mean, we have done lots of testing of ASP13 for different magnitude bins for different countries. I mean, that's why I can send you the results to Norm about the variation of between and within event residues and stuff. And for Europe, it seems to be all right. And also we did some analysis with the Iranian data. For its use in Iran, it seems to be all right. But we have not done any testing or evaluation with the data from California, from Japan, from China. We have not done it. But we did quite a bit of evaluation for different projects with the European database and Iranian database.
I think we need to understand why sigma is higher, and so it would be good to see whether it's tau, whether it's phi, whether it's tau from a lot of events that are poorly recorded, or to understand where it's coming from.
All right. This is my first experience such a project, so I don't know too. I mean, I was in Pegasus, but not in this level. So in that sense, I mean, if you specify me what to do within a couple of days, I can just send you the results.
So I think we need you to go through the residuals a bit, and
All right.
we need to understand how the standard deviations got so large, because that's really the fundamental part of your model that makes it jump out from the others.
Okay. So in terms of, for example, country-based, we did that between event residuals. I mean, that information is ready. I only have to go back and then send you the plots. And the other things, for example, I don't know.
There may be phi and tau and in a few distance bins for
All right.
those.
I have also that kind
and
of
that kind of
information.
a part in is in Bob's and magnitude bins, so we can start.
Okay.
Well versus poorly recorded.
And also I can send you
possibly-
the number of recordings for each earthquake and stuff like that.
Yeah.
So detailed database.
Yeah, to understand whether because for instance, in our model, we estimated tau only from events only from earthquakes that had recordings of at least 5 events. I mean, 5 recordings per event.
Actually, I can say, I mean, Carola has already have the, you have the paper from John Douglas. The table that I presented here, it's a summary of his paper, some from his paper, with some, you can distribute.
Yeah, within the project, all the material can be distributed. So, Bob, you can have a look
You
at
may
this
have some
overview.
answers to those questions in that paper.
This is John Stewart. On the issue of phi, we've looked at 2 earthquakes in the past from Europe, one in Italy, L'Aquila, one from Greece. L'Aquila was 6.4, Greece was 6.5 in 2008. And the phis in those earthquakes are not really different than NGA phis.
All right.
Right, so we've seen the same thing that you see, these high sigmas with a broad catalog, the work with Scacera.
It
But
could
when
be,
we look at particular earthquakes that are well recorded, relatively modern instruments, and there's a finite fault model, and all those sorts of things are in place,
okay.
then we see much smaller phis that seem to be in line, so.
So you mean I mean you suggest like those poorly recorded events inflate the sigma. Is it your suggestion?
Could be,
Could be.
yeah. I mean, I can't get tau from that, right? These are just 2 earthquakes, but I think it's insightful that when you have high quality information, it does seem like
Exactly. I mean
the fees
that
can
kind of analysis I can do them quickly because I have all that material. So the only thing is just sorting the data in different forms.